Hey, hello everyone. Welcome to my class again. Here we are going to solve GATE question paper of 2021, and as I have said previously, I will be solving only organic questions, and for each lecture I will be solving 5 questions. So, today I am going to solve the first 5 organic questions. Interestingly, the first 5 questions of the GATE question paper where the chemistry starts are all organic. So, I will be solving question number 1, 2, 3, 4 and 5. So, the first question says the rate of alkaline hydrolysis, alkaline means in base you are hydrolyzing, for the compound they are asking rate which will react faster, which will hydrolyze fastest, which will be slowest and which will come in between. So, what you are going to hydrolyze here, this is a cyclohexane, is a tertiary butyl is just alkyl group, and this is what is the functional group which will get hydrolyzed. So, amide you are hydrolyzing, ester you are hydrolyzing and again ester you are hydrolyzing. It is asking rate of the reaction. So, first thing is whenever you see question like this for involving cyclohexane, now cyclohexane will not exist as hexagon form because this is very unstable conformation wise. It always stays in chair conformation. So, first thing you do is convert into chair conformation. So, simple thing, just convert cyclohexane into chair conformation. Now, see what has happened is this amide is towards the viewer and this tertiary butyl is also towards the viewer. So, whenever you have something towards the viewer, in the cyclohexane make them above the plane, and if something is away from the viewer make it below the plane. So, here amide CuNH2 group you can see it is toward the viewer, it is coming out of the screen, this is solid line. So, it is coming out of the screen. So, you are the viewer. So, in front of screen out is coming out of your screen. So, towards you, towards the viewer, and this tertiary butyl is also towards the viewer. So, these are two things which is very clear. So, if I number them, this is 1, 2, 3 and 4. So, I will put any in position anywhere, I will start 1. So, 1, 2, 3 and 4. Another important thing what we have to think is this tertiary butyl, you can see here tertiary butyl is very bulky. It cannot and it will not ever exist in axial position, because axial position it faces lot of 1,3 diaxial interaction. So, these two hydrogen is what creates hell for it. So, if tertiary butyl is here, so it will interact with this, it will interact with this and create hell lot of problem, lot of steric hindrance, and therefore, it will not stay in axial position unless you have something like instead of a carbon you put here oxygen, you put here oxygen, then there is no hydrogen, there is no issue, then it can stay in axial position. But if carbon is there, it will have hydrogen axial position, it faces 1,3 diaxial interactions. So, one thing be sure, whatever happens tertiary butyl will be in equatorial position. So, knowingly I chose this position number 4 as here, because here equatorial position is above the plane and axial position is below the plane. How will we know how to put axial position, equatorial position? So, wherever you see the carbon, you want to know on this carbon where will the axial position. See from the neighboring carbons how are we reaching at this carbon. So, to reach here, from here I have to go up, from here also I have to go up. So, the axial bond will be up, axial bond will be up. Similarly, to reach this carbon, we have to go down, we have to go down. The axial bond will be down. Okay, so, axial bond will be down here. And now, if axial is there, equatorial will be on the side. So, here side, here it will be side. Now, when you look at it, what you see? You see axial is up and equatorial is down. So, very clearly here axial is above the plane, equatorial is below the plane. Similarly, here you see equatorial is above, axial is down. So, here equatorial is above the plane, axial is below the plane. So, similarly, here at position number 4, equatorial was above, axial is below. So, here I am putting tertiary butyl, and position number 4 also I have to put this amide now above the plane. So, here axial is above the plane, equatorial is below the plane. So, I am putting CuNH2 above the plane. Now, what happens? Similarly, we will try to draw all the other molecules and then we will see. Okay. All that is said is written here. Now, let us look at molecule number 2. So, here the ester group COET is away from the viewer. You can see because it is dash 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 this line, that means away from the viewer, that means it is behind the screen, it is behind the screen. So, COET will go below the plane and tertiary butyl as such will remain above the plane. So, here we will go with the tertiary butyl same place, and position number 1 what we will do is COET is away from the viewer, so it becomes below the plane. You can see here this is trans, because one is towards the viewer, one is away from the viewer. So, here also you get trans, one is above the plane, one is below the plane. Okay. And then finally the third molecule, again like first problem, both of them are above the viewer, towards the viewer. So, here both of them go above the plane, only difference is in first case it was amide, second case we have ester. So, we have drawn this ester. Now, remember what is very important for this molecule is this molecule's conformations are fixed, cannot flip at all, because whatever happens this tertiary butyl will not go to axial position. So, even little bit of you think something like this is there, it will not happen, it will be fixed on here. So, whatever reactions you have to think from these conformations. You know this cyclohexane generally flips between one form to another form, but here it is so very disbalanced energy wise that it is locked here. Now, it is asking rate of hydrolysis. So, when anywhere rate of reaction is there, no, it is talking about kinetics, how fast the reaction is happening. Now, kinetics depends upon how stable is your intermediate. It is like this, a reactant is there, a product has to form. So, how stable it is? If it is unstable, you have to put more energy, it takes more time for the reaction to happen. If the transition state is stable, intermediate is stable, so little energy, so little less time it takes, little energy you put, it will come back here. So, reaction is faster. So, that is what it is asking. So, let us talk about the transition state. So, here you see this is your amide, it is talking about alkaline hydrolysis. So, OH minus is what is going and attacking here, you get O minus, you get OH. Now, what happens, this transition state, this intermediate is on the axial position. Now, this is very unstable, because this O minus is interacting with those two hydrogens which are in axial position. So, this is called as flagpole interaction, 1,3 diaxial interaction, highly unstable. So, it needs lot of energy to reach here, and therefore, the rate of reaction will be much slower, right. Similarly, same thing with ester also, it involves transition state on top. So, this is highly unstable. So, this reaction will be again slow. But when ester group is in equatorial position, this OH minus comes here. So, this is where the transition state, transition state of the functional group is there. Now, when any functional group is in equatorial position, it does not face any such steric hindrance. So, this is very stable. So, of course, very clearly this second molecule will react much faster than first and third. So, एक चीज clear हो गया, one thing is very clear, second is reacting fastest, and then comes 1 and 3. Now, about 1 and 3. So, first one is amide, second one is ester. Now, I will show you from here. Now, here what happens, both of them have conjugation. You have R, C double bond O, NH2, and you are having R, C double bond O, OET, right. So, now what is happening here, nitrogen is there, nitrogen has lone pair of electrons. So, it conjugates, it basically overlaps with the carbon orbital, p orbital, and then this comes here and you get something like this. What you get is something like this, you get R, C, O minus, double bond NH2 plus, right. So, because of this, what is happening is nitrogen is donating some of its electron density to the carbon. Carbon has p orbital, they overlap. Because of this, now what happens is carbon is getting electrons. So, its hunger for the nucleophile, nucleophile is what is having negative, is hunger for the nucleophile is reduced. So, its electrophilicity has reduced. So, compared to, if I compare with ketone where no such things happen, or compare with aldehyde, amides will be much less electrophilic, nucleophilic reaction will be slower on it. Now, same thing happens with ester also. Ester also pumps electron, this oxygen overlaps with carbon, and a very efficient overlapping because oxygen has 2p orbital, carbon has 2p orbital. So, they mix. So, again this also will be less electrophilic than ketone. But now we have to compare between ester and nitrogen. Now, you know oxygen is second most electronegative element in the periodic table. The first is fluorine, then comes oxygen, and then comes I think chlorine, then comes nitrogen. So, nitrogen much less electronegative than oxygen. So, because that what happens is, look at this nitrogen, look at this oxygen. Nitrogen is less electronegative, so it does not hold its lobe very electrons close to itself. So, the lobe is much bigger when compared to oxygen. Oxygen is very small because oxygen is electronegative, it holds electron close to itself, and because it is much bigger, it polarizes much better, it overlaps much more efficiently than what oxygen will overlap, and therefore, it gets lot of double bond character. See this, lot of double bond character. So, to hydrolyze amide is not easy, you know, you have to put sodium hydroxide, you have to boil it, and it takes a lot of time to hydrolyze amide, but ester is not that tough. You just put sodium hydroxide, little bit stir it, or maybe little temperature, you will be able to get it because this double bond character is much less. Its electrophilicity also is much less. So, nucleophile will not attack. So, here nucleophile will not attack so easily because carbon is getting much more electron from nitrogen than this carbon is getting electron from oxygen. So, attack is slower, and apart from that, breaking this bond, breaking this single bond of CO and H2. You understand the hydrolysis, how the hydrolysis happens. Hydrolysis will happen, this will go on attack, OH minus will attack. Oh, I have not written here. So, basically OH minus goes and attacks here, then this goes up, and this comes down, and then this leaves, and then this leaves. So, this bond has to leave, that is what has to happen. So, if this bond has to leave, if it is weaker, it will leave easier, but when it gets double bond character, this leaving of NH2 becomes tougher, whereas OET is easier because double bond character is much less, as overlap is not that very efficient, and therefore, amide will be the last to hydrolyze. So, the answer is C, 2. In the when the trans ester was there, that reacts fastest, and then ester reacts faster than your amide. So, C is the answer. Let us go to next question. So, next question is, you have an alkene, you have cis alkene, you can see this H is there and this H is there. So, it is Z alkene. Cis we say when we have same group. If you do not have same group, like here methyl is there and here some big group is there. So, we put the term E and Z. E is across, Z is together. How do we do? We give CIP Canning-Gault priority. So, on this carbon there is hydrogen, there is carbon. So, carbon CH3, so first is carbon, first bond leads to carbon. Now, carbon has a more atomic number than hydrogen, so carbon gets first preference, hydrogen gets second preference. Similarly, here again carbon gets first preference, hydrogen gets second preference. So, these are the things. Now, you see 1 and 1 are on the one side, 2 and 2 are on the other side. So, it is Z alkene. So, it is reacting with CH2I2. So, diiodomethane with zinc copper alloy and diether ether is just a solvent, and is asking the product. This is a very famous reaction, you must have got it by now. It is famous Simon-Smith reaction. It is famous Simon-Smith reagent reaction, that is it. So, here what happens is zinc gets inserted between carbon iodine one side. Okay. Now, you know zinc is a metal. Now, metal by definition is electropositive in nature. So, if it is metal, that means it will it will give electron to get positive charge. So, it gives electron to carbon. So, it will get positive polarity and carbon gets negative polarity. That is how the reaction happens. So, negative charge will go and attack here, and then this bond comes and attacks here, and you get a CH2, you get a cyclopropyl ring. So, to make a cyclopropyl ring, Simon-Smith reaction is very, very famous. Now, interesting thing is in this stereochemistry of the reactant is retained, because you can see it is happening, everything is happening from the one side. Now, this alkene, so both of the carbon, you know, this alkene, this carbon, they both are sp2 hybridized, because double bond is there. One of them is sigma bond, that is sp2 hybridized, and one of them will be pi bond, which will be perpendicular to the plane of the molecule. So, that is p orbital, basically unhybridized p orbital, that forms pi bond. So, what happens is, this is trigonal planar. So, one R is coming outside the screen and one is going inside the screen, but it is in one plane. Okay. Similarly, this is one plane and this is outside the screen and this is inside the screen, away from the viewer. So, what happens? So, this both will go and attack CH2. So, this is what is forming CH2. Now, from sp2 it is becoming sp3 hybridized, so it becomes tetrahedral. So, it is coming, so it is pushing this up, it is pushing this also up, but R was towards the viewer. Now, also R remains towards the viewer, R prime is away from the viewer. So, now also it is away from the viewer, same thing happens here and you get this product. So, similarly it will happen here also. So, you are having Z alkene. Now, imagine it on the it is on the screen. So, it is still trigonal planar, but nothing is coming out of the screen. So, this is above the screen, this is above the screen, and this methyl is below the screen, this carbon is below the screen. Now, CH2 will attack. Now, think for yourself. Now, CH2 will come from outside the screen or it will come from behind the screen? It will come from that side which is less hindered. Now, this side silyl, this group is coming outside the screen, is quite hindered. Therefore, CH2 will come from behind the screen. So, when it comes from behind the screen, what will happen? It will push this and this outside, this and this outside, and CH2 goes inside. So, that is what happens, CH2 goes inside and these two stereochemistry is retained, both hydrogens are still on top and this methyl and this group is down. So, the answer is A, right. Next question, the major product formed for the following reaction. So, you are having this molecule and you are putting heat. Second is aqueous acid. So, you would have guessed by now, I am pretty sure. First one is pericyclic reaction under thermal condition and second step is workup, which we have to find out what happens there. So, now it is a pericyclic reaction, it is a nothing but Diels-Alder reaction, it is nothing but Diels-Alder reaction, 4 plus 2. So, 4 electrons are here, 2 electrons are here. So, this is called as diene, because it has 2 alkene group, so it is diene, right. Whereas, this is dienophile, means who loves. So, who loves the diene? So, it has only one alkene. So, this is what goes and attacks this diene, therefore, it is called as dienophile. So, in Diels-Alder reaction, what you have to remember is HOMO of diene, this has been found out by molecular orbital approach. So, HOMO of diene reacts with LUMO of dienophile to give you this product. So, how it happens is, this pi bond comes and attacks here. So, this pi bond is forming sigma bond here. So, that is what is formed sigma bond, that pi bond has gone. So, it has become single bond and this pi bond is coming here. So, again pi bond is lost here, but pi bond has come here and this pi bond goes and forms here. So, it forms sigma bond here. So, you are instead of 3 pi bonds, you are getting 1 pi bond and 2 sigma bonds. And what is very important is HOMO of diene reacts with LUMO of dienophile. HOMO means highest occupied molecular orbital. So, it should have occupied molecular orbital, it needs electron. whereas LUMO is lowest unoccupied molecular orbital. So, it does not need it should be vacant. So, therefore, electron donating group on diene and electron withdrawing group on dienophile favors this reaction. So, electron donating group on the diene and electron withdrawing group on the dienophile is what favors the reaction. Not just that it favors the reaction, it also determines the regioselectivity. Regioselectivity comes from the word region, which side it will attack. So, now you see, if this is pumping, it will push the electron from here to down, so that first attack will be from here, and attack will happen on this carbon because he said electron withdrawing group is there. So, it is getting pulled here and then this comes here. It will never happen that electron withdrawing group is like this, EWG is like this, okay, and then this goes and attacks here. No, that is not possible, that will just not happen. What will happen is electron withdrawing pulls the electron towards itself, and therefore, here positive charge is formed, positive polarity is there, and therefore, this goes and attacks here, and this comes and attacks here, this comes here, and you are getting this kind of species. Similarly, if you have here, so this pumps electron, then this comes here, and then reaction happens. So, in this you are having two pumping group, this OM is also pumping group, this also is pumping group. Okay. So, they pump because of resonance, oxygen is there, oxygen is having lone pair of electrons. So, this can pump electrons. So, it pushes the electron. So, it will come down, this also pushes. So, first attack will be from this side, and initially if you remember Cn was down, see the question, in the question Cs was down. So, you cannot react it like this because it has to accept, Cn has to be top, so that this is what is coming out, and this attacks here, and then this comes out and goes here, and you get this product. Okay. Next step is acidic workup. Now, this is silyl ethers. Best way to remove is just put fluoride, otherwise put to acid also, this goes out. So, you get OH, and then it is still having oxygen lone pair and acid is there. So, it takes proton and becomes methanolic, good leaving group. Then tautomerization kind of thing happens, this comes here, this moves up, you leave out, and you get this product. So, product is C, okay. Fourth question, the least acidic among the following compound. So, first one is alkyne, second one is carboxylic acid, third one is phenol, fourth one is sulfonic acid. Let us look one by one, okay. So, it is asking least acidic. So, in N you are having this alkyne. So, this carbon is what is having this proton, and this proton will be acidic to whatever extent it will be. Now, proton on alkyne. So, terminal alkynes are very lightly acidic. Why they are acidic is because this carbon is sp hybridized. So, if you see sp3 and then you see sp2 and then you see sp, So, what has happened? This one has how much is S character? Out of 4 only 1 is S. So, it is 25%, correct now? It is 1/4, 25%. Here it is out of 3 orbitals 1 orbital is S. So, it is 1/3 or 33%. But here it is out of 2, 1/2 is because of S. So, it is 50%. So, now S orbital has more penetrative effect than p orbital. So, S orbital is closer towards nucleus than p orbital. So, it pulls the electron towards itself, it stabilizes the electron. Okay. So, even if you remove this proton, you get a negative charge. That negative charge is being stabilized by this carbon. So, sp hybridized carbon is more electronegative than sp2 than sp3. So, this proton is slightly acidic, and if you have very strong base, something like n-butyl lithium, you will be able to pull it. So, that is what happens if you remove this proton H plus, you get negative charge, which is getting stabilized because of the electronegativity of this carbon. Why it is electronegative? Because it has more of S character. Okay. Now, in sp3 hybridized carbon, all that is done. So that's why if you put very strong base, something like N-butyl lithium, so it will pull away the proton, you get negative charge Li, then you can further react with whatever you want. Now let's look at N. So this is carboxylic acid. Carboxylic acid is fairly good acids, okay, strong enough, like acetic acid. Organic acids are generally not strong, so this is kind of strong among them. Why it happens is because, see, when I am talking about acidity, you have to always talk about stability of conjugate base. That means if this proton is released, is the species what is left behind is stable. If it is stable, then it's okay, it does not mind losing proton. If it is not stable, it will immediately go and pick up proton. So it will not be acidic enough. But this is quite acidic. Why? Because once proton is lost, you are getting negative charge on oxygen. Oxygen first off is electronegative, it can stabilize negative charge. Apart from that, it will conjugate with the neighboring C double bond O. So this bond comes here, this goes up and you get negative charge on this. So the negative charge is stabilized between two electronegative oxygen atoms. So it becomes half and half. Oxygen will any day stabilize much more than carbon, because oxygen is very electronegative and therefore it is fairly strong acid. So definitely I can say this is weaker acid than carboxylic acid. Next is your phenol. Now phenol also, you remove the proton and look at it. So this negative charge goes and it's getting negative charge getting stabilized on this carbon, then this comes here, it comes on this carbon, then comes and comes here 3 carbon. So basically negative charge is coming over 3 different carbon atoms, and of course oxygen is there. So the negative charge is being stabilized between 4 atoms. So you should say that phenol is more acidic than carboxylic acid, but no. Here the negative charge is on oxygen and then on carbon. Carbon's electronegativity is much lesser than oxygen. So it cannot stabilize negative charge. There 2 oxygens were there, so they both stabilize very efficiently. Here it is still again oxygen is what is stabilizing, carbon very little, but it helps in delocalization, and therefore phenols are less acidic compared to your carboxylic acid. Okay, all that I said is written here. Carboxylic acid is much more stable than a phenolic. Last one is sulfonic acid. Now this is very strong acid. It is like sulfuric acid. If you remove this proton, you get negative charge. Now what happens? Negative charge is stabilized between 3 oxygen atoms. This comes here, you get negative charge, this goes out, comes here. So 3 oxygen atoms are stabilizing this negative charge. Also sulfur is also very big, so this also stabilizes negative charge to a large extent, and therefore this will be the most acidic. So most acidic is sulfonic acid, then carboxylic acid, and then comes phenol, and then last was alkyne. So the least acidic is alkyne, that is M. Now last question is you are having a alcohol on cyclohexane, you are having alcoholic functional group, you are reacting with NOCl, then you are reacting with with light, and then finally is HCl you are hydrolyzing. So forget about HCl, you concentrate only on first 2. So this is the very famous Barton reaction. So Barton reaction, you know, radical reaction, it is used for remote functionalization. So even generally what happens, if you have some functional group, neighboring carbons you can easily functionalize, but far it is very tough. But Barton reaction has this thing where it can do, you know, I did postdoc with Professor David Craich in USA, and David Craich professor with whom he did PhD was Barton. So he was the one who has discovered all these things, right. So first what happens is alcohol reacts with NOCl to give you nitrite NO bond, okay, you get ONO, and then what happens is fragmentation happens at delta carbon. So this is oxygen, so alpha, beta, gamma, and then delta, and that delta, their fragmentation happens so that this hydrogen goes and attacks here and this nitrogen goes here. Why it happens on delta carbon? Because you can see here what you are getting is a very stable 6-membered transition state. 6-membered ring is both kinetically and thermodynamically favored, more so thermodynamically favored. So you see this is interacting with this interacting with this. So if you make something like this dash, it is forming 6-membered transition state. So always ONO is there, so NO breaks up in presence of light, and then it reacts, the oxygen dot reacts with the hydrogen on the delta carbon, remember this. and then you get nitroso group, which again tautomerizes to give you oxine. Okay, oxine is double bond NOH. Now let us look at this molecule. So this OH is there, so this is what will break. Then we said compared to oxygen, from oxygen delta position. So it has lot of delta position here. So let us start from here. Alpha, beta, gamma, this is also delta, and gamma, this is also delta. If I go from here, alpha, beta, gamma, this is delta. Again alpha, beta, gamma, delta. So 4 delta carbons are there. But you understand it needs a stable 6-membered transition state. So which one fits in? This one fits in because they both are in the same plane, they are above the plane. So only this methyl group is what will react. So let us see the mechanism. So OH NOCl is there, so it is all by radical mechanism. This goes out, this comes out, it forms ONO. Now what happens? You are putting light. So in the light, this is what is forming 6-membered ring. See here, 1, 2, 3, 4, 5 and 6. So this oxygen takes away this proton, this carbon gets a radical, and this radical picks up this radical, and you get NO, you get nitroso group, and then tautomerization happens. This comes here, you get double bond NOH, and then under acidic condition it gets oxidized, oxine becomes aldehyde. So your answer is A. So with this I finished the first 5 questions. Thank you very much. Take care. Bye bye.